Welcome to the new era of video creation with Bayo Z8. Today we will discuss about design and deploy an LLM-based chatbot capable of handling real-time customer support for a global e-commerce platform. You are asked to design and deploy an LLM-based chatbot capable of handling real-time customer support for a global e-commerce platform. How would you approach this problem, focusing on model architecture, scalability, latency, and safety considerations?
Building an LLM-powered chatbot for e-commerce customer support requires a deep understanding of both business needs and technical challenges. The chatbot must handle diverse queries related to orders, returns, and product recommendations while ensuring fast response times. Unlike a traditional rule-based chatbot, it needs to be context-aware, understand multilingual inputs, and provide real-time, high-accuracy responses. To achieve this, we must identify key data sources such as historical customer queries, product catalogs, and previous chat interactions to fine-tune the model. The chatbot's effectiveness will be evaluated based on key performance metrics like response accuracy, latency, and customer satisfaction ratings. Ensuring a smooth user experience requires balancing speed and accuracy, particularly when handling large-scale global operations. The first technical decision involves selecting the right LLM. Pre-trained models like GPT-4, Claude, or LLM offer general-purpose language understanding but might lack domain-specific accuracy. Fine-tuning on e-commerce-specific data can enhance performance. For up-to-date responses, integrating retrieval-augmented generation, RAG, allows the chatbot to fetch real-time product information, ensuring that it doesn't rely solely on pre-trained knowledge. This is critical for handling frequent inventory changes and new promotions. Additionally, parameter size impacts inference cost and response speed. While larger models provide superior reasoning, they require more computing power. Deploying quantized or distilled models may help reduce costs while maintaining acceptable quality. Finally, for a global audience, the model must support multiple languages, requiring either a multilingual model or separate fine-tuned instances for different regions. To fine-tune the model effectively, we must first curate a high-quality dataset that includes customer interactions, FAQs, and product descriptions. Supervised fine-tuning involves training the model with labeled data, ensuring it understands common customer support scenarios. Beyond supervised learning, reinforcement learning from human feedback, RLHF, can be used to refine the chatbot's ability to prioritize helpful, accurate, and non-toxic responses. Human raters provide reward signals, guiding the model to favor responses that align with customer expectations. Bias mitigation is another important consideration. E-commerce customers come from diverse backgrounds, and biased model outputs can lead to poor experiences. Strategies such as balanced training data, adversarial testing, and fairness-aware algorithms help reduce unintended biases in the chatbot's responses. Real-time chatbots must deliver fast responses while maintaining high-quality answers. One major optimization strategy is model quantization, where 16-bit floating point weights are converted to 8-bit or even 4-bit representations, reducing memory footprint and inference time. Caching common queries, e.g., "Where is my order?" significantly reduces processing time. If a query matches a cached response, the chatbot can return the answer instantly, bypassing expensive inference computations. For generating responses, efficient decoding strategies like speculative decoding and beam search optimizations help balance speed and fluency. Finally, a hybrid approach can be implemented. Simpler queries are routed to a lightweight model, while complex queries are handled by the full LLM, ensuring an optimal trade-off between speed and accuracy. Deploying an LLM chatbot at scale requires a robust infrastructure. Serverless architectures such as Kubernetes-based deployments allow flexible scaling across cloud resources. Containerized models enable seamless updates and rollback strategies without downtime. For efficient inference, GPU acceleration using TensorRT, ONNX runtime, or Habana Gaudi processors significantly reduces response latency. Running the model in distributed mode with requests balanced across multiple GPUs or TPU instances ensures that customer requests are processed in parallel, reducing bottlenecks. Finally, auto-scaling mechanisms allow the system to dynamically allocate more resources during peak hours, e.g., Black Friday sales, and scale down during low traffic periods, optimizing costs while maintaining service quality. A key challenge in building an AI chatbot is ensuring consistent, contextual conversations across multiple interactions. This requires memory mechanisms that can recall past exchanges within a session and persist relevant customer preferences across multiple visits. For short-term memory, session-based storage helps the chatbot track multi-turn conversations, ensuring coherent responses. For example, if a customer asks, "Where is my order?" and follows up with, "Can I change the address?" the chatbot must remember the context to respond accurately. For long-term memory, storing user preferences, e.g., preferred shipping address, frequently ordered products, improves personalization. Vector databases like FAIAS, Pinecone, or Weaviate allow efficient retrieval of past interactions, enabling the chatbot to reference prior conversations when needed. Managing the context window efficiently is also crucial. LLMs have a fixed token limit, so retaining only relevant context while discarding unnecessary history is essential for optimizing costs and accuracy. Methods like sliding window attention or dynamic truncation help balance memory efficiency with performance. Ensuring safe and responsible chatbot interactions is critical for maintaining customer trust. AI models can sometimes generate toxic, misleading, or inappropriate responses, requiring strict moderation mechanisms. To prevent harmful content, we can integrate toxic language filters such as OpenAI's Moderation API or Perspective API, which detect and block inappropriate responses in real time. Additionally, fact-checking layers ensure that the chatbot does not hallucinate incorrect information, especially when discussing product specifications or policies. Another crucial aspect is abuse prevention. Implementing rate limiting prevents malicious users from spamming queries or exploiting the system for harmful activities. We can also detect bot-driven attacks using anomaly detection techniques. For complex cases, human escalation mechanisms ensure that unresolved queries are smoothly transferred to live support agents. The AI can pre-process customer queries, summarizing context before handing off to a human, ensuring a seamless transition and efficient resolution. To maintain high accuracy and adaptability, an AI chatbot must continuously learn from user interactions. By integrating feedback loops, we can refine the chatbot's responses based on real-world user behavior. One approach is explicit user feedback collection, allowing customers to rate chatbot responses with thumbs up, down. Additionally, automated query logging enables us to identify failure patterns by detecting repeated instances of, "Sorry, I don't know the answer." Active learning pipelines help retrain the chatbot with new, relevant customer queries, reducing outdated responses and improving accuracy. Drift detection monitors changes in chatbot performance over time. If the model begins producing lower quality answers due to evolving customer trends or product updates, it signals the need for retraining. Automating this process ensures that the chatbot remains accurate, relevant, and responsive to user needs. Before deploying a chatbot at scale, rigorous A/B testing ensures optimal performance. This involves testing different model variants, e.g., GPT-4 versus a fine-tuned in-house LLM, to determine which performs best on customer queries. Performance benchmarking includes measuring response latency across different request loads. Metrics like P50, median response time, P90, 90th percentile latency, and P99, worst-case latency, help assess real-time performance under various traffic conditions. User engagement metrics such as average session length, query resolution rates, and customer satisfaction scores provide insights into how effectively the chatbot meets user needs. To ensure safe rollouts, we deploy incrementally, starting with low-risk customer segments. If issues arise, a rollback mechanism allows us to revert to the previous chatbot version, preventing widespread impact. A responsible AI chatbot must prioritize ethics, privacy, and fairness. Compliance with data protection laws such as GDPR, Europe, and CCPA, California, is critical. This means ensuring that customer data is encrypted, anonymized, and only stored when necessary. Bias in AI models can lead to unfair or discriminatory responses. Regular bias auditing, including adversarial testing and dataset diversity analysis, helps identify and correct potential biases in the chatbot's behavior. Explainability and transparency allow users to understand how responses are generated. By offering clarifications, e.g., this answer is based on our latest product information, we improve trust and user experience. Finally, user control mechanisms must be available, allowing customers to review, manage, or delete their chatbot interaction history. This ensures compliance with privacy regulations while giving users greater control over their data.